All right. So lighting systems. This is the first module where we're actually looking at a specific type of system that actually uses energy. So up until now, we've been talking about how do we analyze build energy use? What kind of conclusions can we draw just from looking at a building's utility bills? We talked about some codes and standards and some other base concepts. But now we're finally getting into an actual thing that is going to use energy in our buildings. Lighting systems are often one of the first things that you're going to look at in any energy audit. Generally, the lighting systems use about 8 to 12% of total building energy, which isn't a huge chunk of that total energy use pie. But after you factor out the HVAC, lighting usually comes next. Another reason we often look at lighting upgrades is they generally have a pretty good payback. So if you do a cost versus savings analysis, you've had some homework problems where we've had to do some basic calculations for how fast is this project going to pay back if it costs this much money, but it will save them this much per year. Lighting often has pretty good payback. Utilities also often pay pretty good rebates and incentives for lighting. And these lighting upgrades, because they're generally good and they generally pay back decently well, sometimes this can help pay for other energy conservation measures that maybe don't have very good payback. So maybe you can package a lighting upgrade with an HVAC upgrade, and HVAC upgrades tend to not have very good paybacks, but maybe if you look at it together as one project, maybe the aggregate payback can be pretty good. One other reason that I like to start with lighting as the first system that we actually look at is they're pretty straightforward. So we've talked about how energy use is defined by power times time. If a light fixture uses 100 watts and it runs for 5,000 hours a year, that's a very easy thing to calculate, as opposed to HVAC measures, which tend to get more complicated. So I think lighting is a very good place to start when we are starting to actually look at these energy using systems. Bringing up these CBEX charts, I realize now that might be a little hard to read, so lean into your monitors. The CBEX charts for how much lighting makes up of that energy use pie in an education facility, you can see it makes up about 9%, which again is not a big chunk of the pie, but after you factor out the heating, the cooling, and the ventilation fans, that's the next best thing. This other chunk right here, that's 10%, but that one's a little hard to attack. So lighting is very often the next thing to look at. In an office, it's going to make up a little bit more of that pie at 12%. But then you can get into some other facility types that are a little more specialized, like food service, where you can see lighting only makes up 4%, much, much less. You can see cooking, that's the big one here in food service. And the heating and the cooling and the ventilation fans make up significantly less. And in healthcare, similar to the other buildings, about 9%. Let's start with some basic lighting terms. You already know what watts are. That's how much power input is required to operate a lighting fixture or a motor or really anything. It's just a general power term. One that might be new to you though is lumens. And lumens is a measure of the light output. So you can have fixtures that can put out more or less light, and that's defined as lumens, and that's noted with a capital I. Efficacy, which is a term that we briefly discussed back on day one. So this is the first example of using an efficacy term, which is not the same as efficiency. Recall that efficacy means you are comparing an input and an output that are of different units. So miles per gallon is the most common one. In lighting, what they use is lumens per watt. And a higher efficacy is going to be better because that means you're getting more light output, so more lumens for less power or watts. Foot candles is another common lighting term, which is measured in lumens per square foot. And this is defined as the lighting intensity measured at some location away from that light fixture. Most commonly, this would be measured at someone's work desk. Where are the employees going to be sitting day to day, and what's the lighting intensity at that desk? And this is noted in equations as either a capital E or as FC for foot candles. To help visualize this, so if you have a light bulb in the space, hopefully it's not a um, inefficient incandescent bulb like I'm showing there. You're going to put some power in, so that's the watts input to run the bulb and produce the light. You're going to get some lumens out of that out of that bulb. But what's important here is that lumens output, that is measured at the light fixture itself, which means that that is going to be a constant value for that light fixture that you're going to install. But then what that translates to is the foot candles, which is measured at the usable space. And so your foot candles, that value is going to vary depending on how far away that surface is from the light. So even though the lumens output of that light is a constant value, if you move that light fixture closer or farther away, that's going to impact the lighting intensity in foot candles at the workspace. The relationship there is what's known as the inverse square law, defined as E equals I over D squared. So the translation here, your foot candles, E, is going to be dependent on the square of the distance from the light source. Because the further away you get from the working space, the more the light is diffused and the less lighting intensity you're going to have. And because of that squared relationship with the distance, as an example, if you lower a fixture from 20 feet above your surface down to 10 feet, so you've halved the distance, for that same light fixture, you've just quadrupled your foot candles because of that D squared term. So your I is constant, your D changes, and that results in 4 times as much foot candles. And if you're going the other way, let's say you're going from 10 feet to 20 feet, so you've doubled the distance, now you get a quarter as much light. So this idea of the inverse square law and how lighting intensity at the usable space is impacted by this distance. If you're a lighting designer, this is incredibly important to understand this relationship and know how to calculate this, because there are what are deemed acceptable foot candle levels for different space types. So in an office space, there's a range of foot candles that you want to be in that is considered acceptable. And that could be different than a warehouse where maybe you don't need as much light. But if you're in a laboratory, then you need very good lighting in there. And so each of those each of those space types will have different acceptable foot candle ranges. And there is a potential energy savings opportunity here. Maybe you can lower the height of your light fixtures, drop your lumen output, and drop your wattage to get the same usable light. Ultimately, what we care about as occupants in a building is the foot candles. We don't really care about lumens per watt. I don't care how many lumens a light fixture is outputting. I care about how good is my light at my work desk. And so by playing with the mounting height, you can actually save quite a bit of energy, potentially, if you can do this. So to try to illustrate this a little better, so this is to try to illustrate how the light is diffused radially. And so as that light gets further and further away from its source, it covers a much wider area and is thus, it is diffused by that squared term. So if you're only 1 meter away, you have, well, in relative terms, 100% of your lighting intensity. But then as soon as you're 4 meters away, you're down to 6.25%. Even just 2 meters away, you're down to 25%. So the lighting levels dissipate very, very quickly as you get away from that fixture. So I already mentioned this. It's based on that square of the distance due to the radial output. To throw some actual numbers at this, if we're going to lower our fixtures from 30 feet high to 15 feet high in our space, and our existing lumens that light fixture is outputting is 7,500, and the client says, well, I like the light levels I have today, so I want to maintain the same foot candles. We're going to replace the lights, we're going to lower the lights, but I want about the same foot candles that I had before. So how many lumens do we need after lowering those fixtures? You can use the inverse square law. So our new lumens will be equal to our existing lumens times the square of the ratio of our new distance divided by our old distance. Run through the math, and we would need 1/4 of the lumens. Having the distance, we can quarter the lumen output needed. We can save some good energy that way. Just by dropping that 15 feet, well, now we can go to 1/4 of the lighting output. And this example is expressing it in terms of lumens, but that also is going to be proportional to watts. So maybe we can get down to about 25% required power too. And now we've just lopped off 75% of our lighting power and lighting energy just by making this change. And just to drive the point home, these lumen outputs, whether it's 7,500 or 1875 lumens, ultimately deliver the same foot candles when you measure it at the desk, even though those outputs are very different. Some more terms: color rendering index, abbreviated CRI, which is kind of a abstract term in a way, but it is a measure of how, quote, true colors appear under a lighting source compared to a standard reference. And I'm sure there are all kinds of testing standards that properly define how this works, but ultimately CRI is a measure from 0 to 100, higher being better. And so if you had a lighting source that had a CRI of 90, that would tell you that any objects under that light are going to look very true to the actual color that they are, as compared to another lighting source that would have a low CRI is going to look uh, not like its true color. And we'll go over some different lighting technologies and how the CRI can vary depending on which technology of lighting you're going to be using. There's also correlated color temperature, which might be something you're familiar with or have heard of, but maybe you just didn't know what it was called. But this CCT term is a measure of the light color, which is measured in Kelvin. And here's the scale. So down in the 2000 Kelvin range, so that would be considered low temperature, which is going to give you that warm color or orange or yellow light, versus a high Kelvin up here in the 6000s, also called daylight color, is going to give you that sterile whitish color. And if you've ever bought light bulbs, this can be a pretty important thing. As an example, my wife is very particular about the color of her light bulbs, and she wants every single bulb in our house to be down on this low, warm color end. That just, I don't know, resonates with her, makes her feel warm inside. She absolutely despises this kind of sterile white blue color on the high end. So every time I go and buy light bulbs, if you look at the box, it will tell you where the Kelvin rating is for that bulb and where it falls on this. And usually there's not a lot of variety. Usually there's one option here on the bottom warm end and one option on the white end. But in terms of occupant comfort and how they feel in that space, the color of the lighting can make a big difference. Ballasted lighting systems. A lot of lighting technologies, the way they make light is inside the bulb, there's a gas in there. And when you excite that gas by applying a voltage, that creates light. What's actually going on there, put in very simple terms, when you excite that gas with some electric current, there's a bit of an anomaly there where the resistance of the bulb actually goes down. And if your resistance drops, your current is going to increase correspondingly. And that increase in current means the gas gets excited more and the resistance drops more. And so you end up with this feedback loop where your current is uncontrolled. Your current just keeps going up and up and up, which is causing the resistance to go down and down and down until it gets to the point that your bulb explodes because you're exceeding the amp capacity of what that bulb can handle. The way we fix that is with what's called a ballast. To prevent this from happening, you need a ballast wired to these bulbs. And the entire purpose of this ballast is to regulate the voltage and ultimately regulate the amperage as well. The ballast is often considered the brains of the light fixture. It's controlling it, it's regulating it, making sure it doesn't explode. So very important. There are two types of ballasts. The old school version used a magnetic technology, which worked, and they used it for years and years, and it worked fine, but it is old and inefficient. And as they start to age and fail, really, that can cause some flicker in the fixture. Your lights start flickering, which is super annoying. We don't see a lot of magnetic ballasts anymore. They're largely phased out, but if you go into a really old building, you still might find them. Nowadays, pretty much everything is electronic, which are better efficiency, they're more reliable, less likely to cause flicker, offer more control options. So that's the way we want to go, is toward electronic ballasts, even though that's virtually what most of them, most all of them now are, but you still might run into some magnetic ones. The type of lights that use ballasts include fluorescent, high intensity discharge, and low pressure sodium. We'll go into more detail on those here in a bit, but all of those require a ballast. Here's a very basic wiring diagram for how a basic fluorescent light fixture would be wired. I know it looks very professional. Hold your oohs and ahs. But you have the ballast. That's going to be your primary input device, and that's what you're going to be providing your power into. The ballast has to be in series with the bulbs to prevent that issue of the current increasing and the resistance dropping and then your bulbs exploding. So this ballast takes your voltage input, regulates it, makes sure it's super consistent on the output side so it can actually feed the bulbs the voltage and amperage they need to operate well. But note that these bulbs, they take power to run. So in this case, 32 watts each. This ballast also takes power to run. Not as much as the bulbs, but it still takes 8 watts against the bulbs 64 watts. And the ballast, in terms of energy efficiency or rather lighting output, it's not doing any good. We need it to prevent something catastrophic from happening, but we're ultimately paying an energy penalty there. We're paying an 8-watt penalty to run that ballast, and that's not giving us any better lighting or more efficient lighting, and will actually reduce the efficacy of the entire assembly because it's adding power but not adding any lighting output. So the important thing to note here is that if you have a 32-watt bulb, that doesn't necessarily mean it takes 32 watts to run it. Another term to throw at you, any ballast you look at has what's called a ballast factor, which refers to the ability of a ballast to produce the rated light that the lamp it is powering. So if you look up a lamp and you see, oh, it's rated for 5,000 lumens, then the ballast factor, a ballast factor of 1 will tell you that it'll operate at that lumen output. So let me back up. Important note here. The efficacy of the lamp in lumens per watt is constant. So the lumens output per watt input is going to be constant for that lamp. If you control that bulb with a ballast that has a ballast factor of 1.0, then that lamp will operate as rated. So it will give you the lumens output that's on the sticker when you buy it, and it will take whatever watts it says it'll take. But as an example, let's say you took that 32-watt bulb and you attached it to a ballast that has a ballast factor of 0.85. So this is going to scale both the lumens and the wattage accordingly. So the 2800 rated lumens, now you multiply that by 0.85, you get a little less out of it. You get 85%, so about 2400 lumens instead. On the wattage side, exact same thing. 32 watts times 0.85. Now it's only going to take about 27.2 watts to run that bulb, plus some power for the ballast itself. Let's not forget that. The reason this ballast factor is a thing is that by selecting the ballast and adjusting that ballast factor allows for some fine tuning. So if you're laying out your lighting in a room as a lighting designer, the variable ballast factor allows you to get just a little bit more, a little bit less, because you can't just go out and instead just buy a 30-watt lamp. I mean, there aren't as many options on the lamp side, but with the ballast side, this is the easiest way to fine tune a system. Or maybe you have an architect who says, well, I really want this room to have symmetry. So I want 6 light fixtures 2 rows of 3. I want it to look just like that. And you do the math and you figure out, well, if I put in 6 fixtures like the architect wants, it's going to be overlighted. So let's save some energy, select a ballast with a lower ballast factor, and that'll scale everything down accordingly. So this can be a good way to save some energy as well. This last section might end up leaving a little early today. Don't thank me yet. We're going to talk about some different lighting technologies. I understand this section can be a little bit of a slog, but it is really important to understand some of the differences between the different lighting technologies that are out there. The most basic lamp you can find is an incandescent light bulb. For decades, this is what you found in every single house. Every single lamp had an incandescent bulb. You generate light from a filament in there. Pretty basic setup. Like I said, this has been used for decades. And there are some advantages to incandescent. They are cheap. They do give very good CRI, so that color rendering index. They turn on right away. They distribute light pretty good. You can dim them if you have a dimmable light switch. They give off warm light, a low Kelvin light that a lot of people often like, at least in their homes. But the downsides, they don't last very long. They're really not efficient at all. And they've been getting phased out for a long time. And on that inefficient side, they do generate a significant amount of heat. Now, I have stated in the past that all lighting energy does eventually turn into heat. So you could say 100% of the energy turns into heat. But in the more efficient lighting fixtures, a lot of that heat is coming from the light photons after they've already hit the surfaces. In an incandescent lamp, about 90% of your output is just straight heat, meaning only 10% is actually turning into that usable light. So generally, not a good option, but we're not seeing this very often anymore. A slight step up would be halogen lamps. Similar technology to incandescent. It's still using a filament, but within this housing right here, they've added some particular gases that somehow make it more efficient. I don't know all the science behind that, but they figured out a way to make a bit more efficient incandescent bulb. It has all the same pros as incandescent: good CRI, turns on right away, good light distribution, you can dim them, but they are more expensive. They still don't have a great life. I had a bunch of these exact bulbs in my kitchen some years ago, and I felt like one would die like once a month. It was terrible. Even though they're more efficient than incandescent, they're still not very efficient. So again, not a great option. But when you're going into old buildings doing energy audits, you can still see some of these old lighting types out there, even if we wouldn't put them into a new building. And because of the gases that are inside there, you are supposed to handle these a little carefully, make sure you don't break them. You probably shouldn't just toss them in the garbage. I think maybe you're supposed to recycle them, actually, which is similar to fluorescent. Speaking of which, fluorescent lighting. We talked about fluorescent lighting already when we were talking about ballasted lighting systems. There's some gas in the bulbs. I think it's usually mostly argon. You apply current, creates UV radiation, and ultimately produces light. we still see a lot of fluorescent lighting in commercial buildings, occasionally residential, but this is still extremely common. The good things, they do last a long time. That's one of the reasons why they became so popular. If you think of a multi-story office building that has 1,000 light fixtures, and you think about trying to maintain all those bulbs, you're going to want a lighting system that's going to last a long time, so you're not constantly changing bulbs all over that place. They are a lot more efficient than incandescent and halogen. They light up pretty fast. But the downsides, they do require ballast, which we talked about. So that adds power to them, and that adds maintenance. So every single one of these light fixtures has an associated ballast slapped onto the side of it, or possibly inside this housing. And if the ballast fails, that's another part that they have to replace periodically. So that means you have to keep spare ballasts on hand. So that can be a hassle. Generally, these aren't dimmable. And if you're going to toss them, you're supposed to recycle them. The main reason being that they contain mercury. You're not supposed to just throw these away. You're not supposed to go in the back alley and play Jedi, lightsaber fights with them. It's not a good idea. You're supposed to recycle them, which is a pain. A quick side discussion on fluorescent terms, because fluorescent lighting is still very prominent in commercial applications. When you're talking about fluorescent, the most common designation for how you talk about fluorescent lighting is by using these T terms. So T5, T8, T12. Those are the only three I know of, but there might be some other oddball ones there. What this is referring to is the bulb diameter. So you got this long tube that is some diameter, and that's measured in eighths of an inch. So a T5 would be 5/8 diameter, a T8 is 1 inch, and a T12 is 1.5 inch. Seems like kind of an odd way to measure, but that's the way the industry is. The common way to tag the bulbs is F, and then the wattage of the bulb, T, and then the size of the bulb. So some examples, F32 T8 tells me that that light fixture has 32 watt lamps and they're 1 inch in diameter. F40 T12, 40 watt lamps, 1.5 inch diameter. F21 T5, 21 watt lamps, 5/8 inch diameter. Next up is compact fluorescent, commonly known as a CFL. Exact same technology as a standard fluorescent system. It's just they've integrated everything into this bulb. So this bulb right here, that you probably have some of these around your house, within this base is a ballast. You still have to have a ballast. It's still operating on the same principle. The advantage here is this is all integrated into one piece, and really you can replace any standard incandescent bulb with a screw-in CFL. The advantages are exactly the same as fluorescent light fixtures. They last a long time, much more efficient, they light up pretty quick, easy to replace incandescent with CFLs, but they have the same downsides. Generally not dimmable and also require special disposal because of the mercury. And really, these are getting phased out as well, because now LED bulbs, which we'll get to that here in a few minutes, now you can buy screw-in LED bulbs for pretty cheap. So CFLs are getting phased out as well. High intensity discharge, HID. This is very similar technology as fluorescent. It's doing the same thing with exciting a gas to produce light. The difference is these are often used in high bay areas where you're putting the light very high, but you're still wanting to get good light down below. This comes in a few different flavors: mercury vapor, metal halide, and high pressure sodium. You'd have to ask a lighting expert to get into the specifics of how all of those are different, but they're functionally operating on similar principles. The pros: they last a long time, which is good when you're putting these in a very high bay area, because if you have a bunch of these bulbs that are 30 feet off the floor, those are a pain in the butt to replace. So, hey, let's buy some lights that are going to last a long time. They're pretty efficient and they do provide good light distribution, which is why they work well in these high bay scenarios. But the downsides: they don't have very good CRI. And maybe that's not important in most applications where you might see these. So outside in this loading dock, I don't think CRI is much of a priority here. Who cares? One big disadvantage is these take a long time to relight. I've seen HID lighting fixtures in school gyms where, again, they're 30 feet off the floor, and the maintenance people, once they turn those lights on in the morning, they just never turn them off because it takes a good 10 or 15 minutes for them to warm up and actually produce the light. So that's not great from an energy savings perspective, leaving the lights on when nobody's there. And because these operate on similar technology as fluorescents, they require a ballast. So added maintenance, added power requirement. And one thing that's a little unique is they have what's called poor lumen maintenance. Any light fixture you buy, the lumen output, earlier I said it's constant, which is not technically true. Over the years, the lumen output from that fixture will actually drop off a bit over time. And some lighting fixtures are better about it than others. HID is one of the bad ones. So that output's going to drop off over time, which may or may not be important depending on where you're using them. Low pressure sodium. So I mentioned one of the high intensity discharge lighting types was high pressure sodium. This is low pressure sodium. Again, similar technology, exciting a gas. Also often used in high bay areas, similar to high intensity discharge fixtures. This does have a bit more limited applications due to the extremely poor CRI. So the way you notice a low pressure sodium fixture is that orange glow, which you can see in that picture. It just looks kind of gross. But there are some reasons to use this. They actually do have a very high efficacy. So you get a lot of light output for not a lot of power, which ultimately leads to it being inexpensive to operate. And compared to the high intensity discharge, these actually have pretty good lumen maintenance. So they're going to maintain a fairly consistent output over time. And these are all reasons why we see a lot of low pressure sodium in street lighting, like in this photo. Because the city, they might have thousands or tens of thousands of light fixtures out there on the streets. And again, thinking of the maintenance, well, you still have to deal with a ballast, but they're going to maintain their lumen output over time. So that's good. And they're inexpensive to operate, which is also good considering how many they're going to have. But there are some downsides. They do cost a little bit more on that first cost, and they give that really gross orange light that's just a terrible CRI. And they require a ballast, just like all those other technologies that we've already talked about. Another part to maintain, and adds power to the light fixture without increasing the lighting output. Last up, and then I can let you go, LEDs, light emitting diodes. So there's no filament like you have with incandescent and halogen. You don't have a gas like you do with fluorescent and high intensity discharge, low pressure sodium, and there's no ballast. An LED is just a semiconductor. That's a particular material that when you apply voltage to that semiconductor, it produces light. For years and years, we've had LEDs. I mean, if on your laptop or your desktop computer, there's probably a handful of LEDs there that are blinking and telling you that the computer's on or that the CD drive is running. We've been using LEDs for a long, long time, but it took a long time for LED technology to get to the point that we could have bigger light fixtures. For a long time, it was only cost effective to just have these tiny little LEDs on computers and other electronics. But now we can produce these very large light fixtures at a reasonable cost. The advantages of LED, they have very high efficacy, meaning high output for low power, which means they're inexpensive to operate. They do last a long time, at least if you buy it from a reputable company. There's really no maintenance to speak of on these. There's no ballast you have to maintain. LEDs are essentially plug and play. They're just supposed to work. And once they're working, you're just supposed to leave them there until they eventually die. And they have a very high color rendering index, and they're usually dimmable. So all of these great things about LED fixtures, but the big downside, the reason why we're not seeing these everywhere, is they have the most expensive first cost compared to all of those other technologies. But they are closing the gap every single year. I've been I've been in this energy auditing uh, world, let's say, for 10 years. And when I started with McKinstry, we didn't do any LED upgrades. All we did was high efficiency fluorescent. So we would go into a building that maybe has old, inefficient T12 fluorescent lighting, and we'd go back in with T8 fluorescent lighting that would be um, more efficient and have a higher efficacy. We just never saw LED upgrades. But then year after year, the cost of LED light fixtures came down, and now it's, I'd say we probably have more LED upgrades than anything else. So it's probably going to get to the point that anytime we're looking at a lighting upgrade, you're doing LED. And just because that is what makes the most sense. But again, you walk into an old building, you still need to be able to identify that, hey, you got low pressure sodium fixtures up there, or you got metal halide fixtures up there. I can't really explain or teach you how to identify that. Even I have trouble unless it's low pressure sodium and it's got that orange glow. But we do have in-house lighting experts, and when they tell me, oh yeah, they got metal halide fixtures, I know what he's talking about. With LEDs, they do approximately have the same general efficacy as fluorescents, which might sound a little odd considering I just explained how efficient these are and how LEDs are becoming the go-to lighting technology. The difference is LEDs are directional, whereas fluorescents are not. So when you have a fluorescent bulb or a pair of bulbs, because they're usually paired up in parallel, when you excite that gas in the bulb, it produces light in every single direction. That's all it knows how to do. It just produces light inside the bulb, and it just goes out 360 degrees all around. With LEDs, it only goes in the direction that it's pointing at. So LED is a directional lighting technology. And with fluorescence, what I didn't show in the diagram here is if you have a fluorescent bulb, usually mounted on the top of this is a reflector. So a piece of metal that's kind of a upside down U shape where the light will hit that reflector and then be reflected down into usable light within the space. But every time light is reflected, some energy is lost. So it's, even though you're getting some of that lighting output to the usable space, you're not getting as much as you really want to, just because every time it reflects, you're going to lose some of that energy. Whereas an LED fixture, that's just outputting light in the direction you want. So it's really able to focus the light to the place you want it, which means you can ultimately get away with less power and save energy. So yeah, able to deliver more light direct to the work surface as opposed to losing light within the fixture. I already mentioned LEDs are growing extremely fast. It's becoming much, much more prominent, and pretty soon this will be the go-to technology for any lighting upgrade. That's all I got for lecture. Any questions?
What would Christmas light be considered?
Well, um, you can buy different types. So if you go to the store and you look at their Christmas lights, you're probably going to see incandescents in one area, and then you're going to have LEDs in another area, and the LEDs are going to be more expensive. What we've noticed is the LEDs tend to be a lot more reliable. So after many years and many failed light strings and hours of trying to troubleshoot, well, which bulb in this 100 bulb string is the bad one, now we just buy LED bulbs and just pay that premium knowing that we'll get hopefully at least one more year out of them. The cheap incandescent Christmas lights, I feel like we get 1 year out of them and that's it. But eventually we'll probably get to the point that they will probably start phasing out the incandescent version of Christmas lights.
Fascinating. Thank you.
Well, we got about 20 minutes of spare time. So if you want to keep working in the background, I'm happy to hang out. Otherwise, have a good night and I'll talk to you Thursday.